on the Zoom screen.
Wonderful.
Okay.
Yeah.
Anyway, now we need to start. So
yeah, we need to start. Hang on, just 1 second, because I start the streaming.
Do we start at 3 or 3? I thought
I'm going to start. I started streaming, but it just comes in a second. I turned it on here. It says that it's streaming, but I have to turn it on, and then I have to mute it, because otherwise, there you go. Now I mute myself. It's 20 seconds delay, and I'll go ahead and start. I think we're all here more or less. Let me share the screen real quick. So once again, thank you everybody for being here. Let me begin, and we'll come back after 2 weeks hiatus because of the 2 workshops, one that we have to organize in SPICE and the other one Intermag. So they may, just as everybody knows, this is a Zoom webinar format where the participants are listening to and viewing the actual screens on the speaker itself. And then please write your Q&A, and the Q&A, write the questions. The chat can work, but it's better to write in the Q&A. That way we can actually afterwards organize it better, or raise your hands, and then I'll try to get to you as well. Just as before, please keep in mind to watch the seminar series. We try to keep it every week. Some weeks may not be in the summer session, but we will see. I'll try to find good speakers for you. And next week, for example, is Karen Evershore, who unfortunately is not here at the moment, so may come in a minute, and who is going to be moving to Duisburg, as some of you may know already, as a W3 professor. Just briefly to introduce somebody that in our field doesn't have much of introduction, Ulrich Nowak is a world expert on magnetomagnetics, magnetomicroscopics. However you say it, I forgot. I think I need my coffee today. And he has been doing the great work on modeling very non-trivial physics in magnetic systems in particular, and really having one of the best computational tools in our field. Has many awards. He's been elected to the Senate of the University of Constance, senior member of the IEEE Society. I thought you were one of the lecturers at some point, and then head of the Department of Physics for a while. Unfortunately, into 2020, hopefully now is over, and then now you have more time to do physics. So with that, I will ask you to stop sharing here. And Ulrich, please share your screen and begin your talk whenever it's convenient. Let's see if Karen is here. Okay. Yeah, about Karen.
Okay, can you see that?
Yeah, we can see it perfectly. Okay. So we'll mute ourselves and then just go ahead. Thank you.
Perfect. So thank you very much, Jairo, for the nice introduction, and also for inviting me here to speak in this seminar. And yeah, when I thought what would be a good topic, I thought let's talk about the Landau-Lifshitz equation, because that is such an important equation in magnetism, and it is used so much, and it has so many different interpretations. And so that will be my topic. But I start with an explanation what I'm not going to do. So I will not give a history of that equation, starting with the work from Landau and Lifshitz. I will do rather the opposite. I will talk only about very progressive modern work that was done in my group. And I will do that in 3 steps, let's say, in 3 steps. After an introduction, I will start with the applications of the equation itself in terms of orbital resolved spin models and the implementation of the inverse Faraday effect. In the second part, I will go beyond the Landau-Lifshitz equation, because there is recent work on extensions of the equation. And I will pick 2 examples, namely the field derivative torque and nutation. So that's beyond LHE. And in the third part, I will not use the LHE at all, but I will talk about phonons, because there's a transfer of spin angular momentum into the phonon system. And the angular momentum of the phonons is also an interesting property. So we'll talk specifically about that. which is not connected to the Landau-Lifshitz equation, but it should be connected. And in the last slide, I will give some outlook how to connect spin and phonon dynamics. Let's start with an overview, modeling in magnetism, since this is a theory talk. So I made up this slide. Don't think too much maybe about it. So I just put down a couple of methods that are used in theory of magnetism, and I sorted them along this axis here according to degrees of freedom, from electrons to spins or atoms, continuum theory, and quasi-particles like skyrmions or so in Thiele equation. And along this axis here, according to methods, or what you could do with it, let's say. For example, first principles calculation, you calculate static properties. Time-dependent DFT would be dynamic, and then thermodynamic would mean that you put in the thermodynamic aspects or the statistical physics aspects to describe some properties. And Landau-Lifshitz equation with spin models is somewhere here. But I will come back to that point a little later, because first I want to give a motivation. So what are trends in magnetism currently, and what is it what you want to describe as a theoretician? So just some motivation. I think one of the driving forces in science at the moment is climate change, because it's one of our tasks in the future to save energy. And that is maybe the most important driving force at the moment. Here are some numbers I found in the internet. Data centers, for example, cloud storage or so, takes a lot of energy currently. So here it says 7% of the commercial electric energy consumption in the US is now data centers. And that was only 2013, and numbers are going up. So electronic devices take a lot of energy. It might be something the young people don't want to hear, but it's true. Smartphones and all the equipment that is connected to that take a lot of energy. And that is one driving force to look for new technological developments to save energy. That means, for example, one could try not to use pure electronic devices in the future, but devices that exploit new ways of transport, not electron transport, charge transport, but maybe spin transport or combinations of that, electron with a spin, or maybe just spin transport in an insulator. Even that is possible, because spin can also be transported as a magnon. So one could use insulating materials for transport properties, and with that saving energy. Then there are other trends to look for new materials. One could possibly store information in antiferromagnets. Those were considered rather useless before because they don't have magnetization, but recently ways were found to read antiferromagnetic domain configurations and also to write in certain types of materials. These are rather special materials. The crystal structures have to break inversion symmetry, so one has to know where the atoms are to understand what is going on. So one needs a very detailed microscopic understanding for these effects. And then there's, of course, this trend to write information optically with light, much of the work going back to the group of Theo Rasing, and I will come back to this to these things during my talk from time to time. So that's ultra fast, all optical switching. Also, that is considered to save energy, but it's also ultra fast. So it's much quicker than normal writing procedures. So if we now go back to that slide that I showed you before, one might gain some understanding what is important at the moment. It is certainly important to describe antiferromagnetic materials atomistically, to understand the symmetry aspects, for example, if you break inversion symmetry, or to understand topological aspects. So you need a detailed modeling where the spins or maybe the atoms are the degrees of freedom. That is important. And of course, it's important to combine that somehow with first principle calculations, for example. And I will show this, what is now marked red here during my talk. I'm also working on other aspects in my group. I'm interested in everything. I mean, the combinations of different methods, also how to go to Landau-Lifshitz block equation or Thiele equation. But now in that talk, I will I will talk about this here: microscopic understanding, spin models, first principle calculation, also a bit of molecular dynamics to get some knowledge of the coupling of spins to the lattice, spin-phonon coupling. Here we go. So that is the famous Landau-Lifshitz equation, which you have certainly seen before. I mean, historically, that was more applied in terms of continuum theory, where you were coming from a microscopic picture with atoms and magnetic moments on the atoms, also you average somehow to a magnetization. Then you might later on discretize for numerical reasons, but it would be a continuum theory for the magnetization. You can write down the energy functional for the magnetization. You will have some exchange energy, anisotropies, an external field, magnetostatic energy, and then you would solve the famous Landau-Lifshitz equation, which has a precession term and a dissipation term here. The effective field that enters here comes from the energy that you use. If you do that, you can solve certain problems, can calculate domain configurations and some dynamics. Of course, the thermodynamic aspects, thermal fluctuations is also interesting. There's some work already from the 60s from Brown to add a stochastic field. However, if you do that, you will not really get thermal equilibrium properties properly, at least not at elevated temperatures, because for that you would need to calculate, let's say, Mach-nons with a realistic dispersion relation, but for that you need a lattice. So because of the continuum theory, the spin wave spectrum will not be correct, at least on smaller length scales. That was pointed out here in this paper. One can improve that, of course, going to a spin model, which relies on the real physical lattice of a given material. And that could be rather complicated. I have an example here in this picture, which is a bilayer. It's a Heusler alloy with a ferromagnetic layer on it. The Heusler alloy is nickel-based. It's an antiferromagnet. So you see how complicated a spin structure could be. You have two sublattices in the antiferromagnet, and then the layers of the ferromagnet. You have interface effects and so on. You can all try to describe that in a spin model, giving each of the atoms a magnetic moment, and then you can express somehow an energy which looks like that. It has the same somehow corresponding, let's say, energy terms that we had before. There will be some exchange energy in anisotropy, a field. The dipole-dipole coupling takes over the stray field energy. And then it can be rather complicated. You could say that the isotropic exchange here, that would be a Heisenberg model, might be extended to this relativistic effects. Then you get Jaluzinski-Moria interaction, other anisotropies, two-side anisotropies, and so on. That can all be decomposed. That's nice. You might be able to describe such a model. The problem is that, maybe we go back once, that you end up with a lot of parameters, because you would have all these parameters, interaction in that picture, for example, layer-wise, because the interface will have some effect, interface anisotropy, symmetry breaking, you get Jaluzinski-Moria, and so on. And that will be all layer-wise, and it will be realistically more than nearest neighbor interaction. It might be next neighbors and so on. So that's a rather complicated thing. But what you can do to get all these parameters is to build a bridge to ab initio calculations, to get them from first principles. That goes back to work here by Lichtenstein and Katz-Nelson already from the 80s. They derived the first formula how to calculate an isotropic Heisenberg exchange from first principles with DFT calculations. And as a side remark, that was already orbital resolved. That's interesting. I will come back to orbital resolved models later. But that original formula is already a sum over orbits. So the magnetic moment of the atom is decomposed in the different orbits of the atom, and the total interaction is calculated as a sum. Yeah, and then there are, of course, extensions of that work. It was developed a lot further, partly by Laszlo Szynjog. He's a collaborator of mine, so I mention his work here. to get relativistic interaction, including Jaroszynska-Muria and anisotropies, and that for layered system interfaces and so on. The result could be like here, shown on the right side. That's just one example, a recent work of ours, where we also compared with experiments from Manfred Albrecht on iron platinum with chromium in it. And then, of course, that's a complicated material, so you get all sorts of interactions, pairwise, iron, chromium, chromium. Some are negative antiferromagnetically, some are positive ferromagnetically. They are nearest neighbors, next nearest neighbors, and so on. So that is something you cannot just fit to experimental factors. So you need some knowledge to get all these parameters. But once you have them, you can implement them, of course, in a spin model. And then another trend, building a bridge to initial calculations, is to include optomagnetic effects. And much of the work there has been done by Peter Oppenaer. There's this work by Marco Berita, for example, to get from first principles, for example, inverse Faraday effect constants. In the following, as an example, I will have gadolinium, terbium, and chromium, platinum. They will pop up in the following. Where we have a spin model that is based on first principle calculations. And then, once again, you need an equation of motion, and once again, you use the Landau-Lifshitz equation, of course. And on that level, it's much less phenomenological, because you can easily derive the first part from Heisenberg's equation of motion. So that's no longer phenomenological. And even the second part has been derived meanwhile by some calculations, for example, also from the group of Peter Oppenaer. You have the same form of the equation with precession, dissipation, of course. And then you add, once again, fluctuations to the effective field so that you get coupling to the heat bath. That's good, call that Langevin dynamics, because you have dissipation, friction, you could say, and you have fluctuations. You have to make assumptions about the noise, usually that it's white noise, and then you can calculate the properties, the strength of that noise, which is related to the temperature. There's a lot of work going on even in that field, by the way. You can try different types of also correlated noise, so which might be more realistic. Anyway, once you have that, you can solve these equations numerically. That goes back to work from Roy Chantrell. We started that in the 90s or so. And nowadays it's possible to simulate like 10 to the 8 spins or so, solving the stochastic differential equation. And you get that equilibrium properties in the canonical ensemble. Here, once again, just an example, the equilibrium magnetization of dysprosium cobalt. That's a rather complicated material. It's a ferrimagnet that has a compensation point and a reorientation transition. Both thermal, just thermodynamic aspects that we calculated from a spin model. That's work with Lasso Sinyok's group. There are some advantages and disadvantages. You get realistic dispersion relation with that method. Maybe to mention one disadvantage, you do that now in a classical approximation. That means you treat the spins as unit vectors. And that means you, in a Magnon picture, you do not get the quantum mechanical distribution of the Magnons, so Bose-Einstein, but you get the classical approximation, really genes, which is the approximation of high Magnon density. So that means something should be wrong here in the low temperature regime, for example. Okay, so now we have a method. That was the introduction, and let's see. Step one, let's apply this method to two examples. And that is work that is done in collaboration with a group of Peter Oppenaer, Karel Kava in Prague. They did the ab initio part. Then I will show some measurements from the group of Martin Weinert in Berlin. And these are the people in my group. The one part was mostly done by Andreas Donges, and the second part, chromium platinum, by Tobias Dannegger. Okay, that refers now to ultra-fast spin dynamics. And the first point one is to work on is the demagnetization. So that is known since the 90s, the work of Bourrepaire. You can demagnetize ferromagnets in less than a picosecond, 100 femtosecond with a laser pulse. And there's lots of aspects of that which are still not understood. I mean, some understanding in the original paper came from the idea to use a 3-temperature model to say that electrons, phonons, and spins are not in equilibrium on that ultra-fast time scales. And you heat the electrons, and then the spins somehow follow, and the lattice will cool the whole thing somehow again down until they are in equilibrium. One open problem here is, as a side remark, the flow of angular momentum. 3-temperature model treats the flow of the energy. But one would also assume that there is angular momentum conservation. The question is, how does the angular momentum of the spin system go? I mean, where does it go on what time scales or so? And that I will talk about that in the last part. But here we will start just with the demagnetization. Because there are, of course, lots of experiments done. There are more or less sophisticated, and very sophisticated of that was done in Berlin recently by Martin Weinert and his group, because they investigated gadolinium and terbium, and they made a concurrent measurement of the parts of the magnetic moment that come off from the D and S electrons and the F electrons. They could separate that. And the results are quite different. If you look into gadolinium, what you see here is that the F magnetic moments, or the moments from the F electron, demagnetize much slower than those of the D electrons. While in terbium, that is practically parallel. So why is that? I wrote already here excellent agreement with theory, because the lines are a theory. That's now simulation. So we tried now to calculate distinct dynamics of D and F electrons, let's say, or spins. And it agrees. Okay, but how did we do that? We made a model that is a spin model. That's not my best slide, I fear. Sorry, but it is a spin model that distinguishes magnetic moments coming from the F electrons and from the S and D electrons. And that can be calculated, all the model parameters can be calculated from first principles, and that was done by Karl Kawa and Peter Oppenair. So they calculated the interaction. There is none between the F electrons, no exchange, but only between D, but there's an intra-atomic exchange, and that all you can calculate from first principles. And then you have to make some model assumptions. It's rather complicated and detailed. I'm not going to the details here. Roughly, you calculate a 2-temperature model and estimate the electron and the phonon temperature, just phenomenologically. In practice, it's a bit more difficult because the cooling by the substrate plays a role. So we had to also model the heat diffusion to the substrate. And also the spin system cools the phonons slightly in the electrons. So it's not just a heat bath. You have to treat really the heat transfer between the 3 degrees of freedom. But you can do that, and then you can calculate the dynamics. And then you get indeed the results that I've shown you. And now the question is, why does gadolinium have a distinct dynamics and terbium not? Because most of the parameters are rather similar. Exchange intervals, they are not really very different. The intra-atomic exchange is also nearly the same. There's not much difference. The main difference is indeed that coupling here, from the F electrons to the lattice, let's say. And the reason is that that is spin-orbit coupling, but there is no orbital moment in the gadolinium, but in the terbium. That leads to the fact that this coupling is stronger than that. And that leads to the fact that terbium demagnetizes much quicker because it is heated by the phonons, interestingly. It's not heated by the electrons or the coupling to the D spins, because that is the same in gadolinium. It is this path that is really different. And for that reason, the terbium demagnetizes, but the gadolinium not, at least on very short time scales. And the second part here, what you can treat with as an example with the Landau-Lifshitz equation, is the inverse Faraday effect. That is a very interesting effect, which is thought to be responsible for all optical switching, at least in some materials, let's say. And that is rather complicated. There are many materials, many effects, and different interpretations in the literature. but it is a fact that you can write into certain materials helicity dependently just with a laser. And there are all the examples. I show this here because we did some theory here. That's rather recent work from Markus Münzenberg's group here in iron platinum. So you can write, you can even rewrite. And the details of the effects are maybe not completely understood, at least not in all materials. But we think it's the inverse Faraday effect, and the inverse Faraday effect induces magnetic moments, helicity dependent, and that makes some effect. By the way, there's much dispute in the literature, but I think there's some agreement. All these, at least all models that can explain these effects rely on a linear switching. That means the material is so much heated during the writing procedure that it demagnetizes during the reversal and remagnetizes on the other side. So it's not really a precessive writing procedure, keeping the magnitude of the magnetization constant. It's rather linear, it demagnetizes. Now we asked ourselves the question, what about antiferromagnets? So what is the inverse Faraday effect in antiferromagnets, and what can one do with it? And we did that as an example for chromium platinum, because it's similar to iron platinum, which is well investigated, but iron platinum is a ferromagnet. So this is an antiferromagnet. It has two sublattices, like that. In the ground state, it's an L10 structure, so you have platinum layers. And then in the group of open air, they calculated the inverse Faraday constants for that material. And what comes out, in short, is, interestingly, that the induced moments are staggered. You can see that also in that graph here. That is the inverse Faraday constant. It's frequency dependent for the two helicities. And the main point is it depends on the sublattice, parallel or antiparallel to the k vector of the light, and it's positive and negative. So it points in different direction. It's staggered. So it points, for example, here always in the opposite direction to the spin structure. That was red, golden here, and the staggered moments are here purple and blue. So you can do something with that. One could naively think the inverse Faraday effect is 0 or so because the effective field is 0 because the magnetization is 0, but that's not the case. It is sublattice dependent and staggered. And by the way, small in the transverse geometry, then it's practically 0. So now what happens if you simulate that? We did that in the following way. Like before in the other example, we calculate somehow electron phonon temperature for the laser pulse. We solve the Landau-Lifshitz equation. Our model now has to include the inverse Faraday effect. And we did that by calculating the induced moments via the inverse Faraday effect constants from Peter Openair. Then we add it to the magnetic moments that are already on the sublattice. Then we somehow renormalize all equations. And then we get a correction to our, what we call spin, the unit vector. And that is added in the Hamiltonian like that. That part here is time dependent. So only during the effect and maybe a bit longer, there will be an induced moment, then it vanishes. And the effect is then mostly the interaction with the neighbors, because you have an additional spin that interacts with the neighboring spin. That's it. There's one open parameter, I must admit, because the inverse Faraday effect, these induced moments will have some dynamics. That's this red line here, times 100, by the way. And we assume that it comes up with the laser pulse intensity and then decays exponentially, and we treat this exponential decay as a parameter. We vary a bit, some 100 femtosecond or so. It goes from practically nothing to some 100 femtoseconds. The effect, by the way, in numbers is small. This is times 100, so it is like 1% or so. It's a tiny moment that is induced, but because of the exchange, it has some consequences that are shown here. Maybe I go back once. So this is an example where the sublattice magnetization, or the nail vector, you could say, indeed switches. No inverse Faraday effect blue, nothing happens, some demagnetization, then it goes back. With the inverse Faraday effect, it switches. That's this line here. But that is a stochastic event, one could say. So there are thermal fluctuations, and it might also happen that it does not switch. So that is normal, I would say. If you have small effects like an inverse Faraday effect, you get probabilistic switching, and you have to investigate that accordingly. And that is the probability of switching versus laser intensity. Transverse, that is like a test, that is zero effect. Zero effect means it does not switch. For low laser power, for higher laser power, you heat a lot, and then you get just thermal heating, superparamagnetic switching, you could say. So the probability then is 1/2. So that's useless. You could say that is zero effect. But with the inverse Faraday effect in longitudinal geometry, you get some effect. And depending on the assumptions, how big the effect is, and we scaled it here. So with the 1, that is the effect from the how it was calculated initial-wise, we would say there's a probability of close to 1 for some laser powers here. So there should be there should be deterministic switching for optimized situations. And that is the most complicated graph I should probably, that shows how it switches. I mean, the details are not easy to understand. The point is, this is not a linear switching. The system does not demagnetize here, in contrast to all the other materials that we simulated for switching. Iron platinum, for example, for the same, let's say, material or similar material parameters and laser intensities, iron platinum would demagnetize and come out on the other side, linear switching. But chromium platinum, it doesn't demagnetize, it really switches as a rotation of the Néel vector. It's not really keeping the magnitude completely constant, so we say it is elliptical switching also. But it's not demagnetization, it's really a rotation. And why that is so quick, because it takes less than 500 femtoseconds, that is because the switching is exchange enhanced. That happens often in antiferromagnets. What happens is, in a nutshell, the induced moments and the effective fields lead to a canting of the sublattice magnetization of the two sublattices, because they point in the same direction. And because of the canting, you have an exchange field, and that leads to the precession of the motion until it ends up in the reverse state. And by the way, you could say for an experimenter that seems rather useless, because you switch the Néel vector, but with slightly different assumptions, and for lower laser intensities, you can also get 90-degree switching, and that would be more interesting because that is measurable. With that, I come to the second part, that is beyond LRG equation. And that is work that is on field derivative talks and notation. That's both with Peter Oppener and most of all with Ritwik Mondal, who was in Peter Oppener's group as a PhD student. Then he came to my group as a postdoc, and many of the ideas and extensions of the LRG equation were then implemented in my group, in our codes, and we played around with that. And now he is, since recently, beginning of the year, in Prague. And the people in my group, Sebastian Rosenbach, Levente Rocha, work mostly on that as well. And that refers, the first example now, field derivative talk, refers to terahertz radiation. So I have as an example here of the work from Tobias Kampfrath from 2010, who showed that in the antiferromagnet nickel oxide, you can excite magnons with a single cycle or sub-single cycle terahertz laser pulse. And then we took that idea and simulated that and looked what would happen if one would have much larger fields. So that's excitations due to the B field component of the laser light. So if that would be much larger, like 10 times larger, what would happen? And we showed then the Néel vector could indeed switch. That's once again a rather complicated exchange enhanced motion, but anyway, you see the Néel vector switches. But that is also rather old already, from 2013. But meanwhile, there have been extensions to the Landau-Lifshitz equation that we considered here, and that is field derivative torque. That goes back to work from Ritwig and Peter Obner. They derive the Landau-Lifshitz equation from basic principles, mostly the Dirac-Kohn-Sham equation, and then you can derive an effective equation of motion for the spin system, let's say, that contains relativistic effects. And what you end up in a nutshell with is the Landau-Lifshitz equation. So one could say now it's derived from first principles, let's say, or basic principles, including the precession and the relaxation term. And there are now expressions for the damping constant. There are also other expressions for damping, by the way, from other authors, I should say. It's also anisotropic, but you also get additional terms. There are more than these, many more, several more, let's say. And one of them is the so-called field derivative torque. And that was implemented in my group. That means that because of these relativistic effects, you get also components of the effective field that go with the time derivative of the field. So if you come with a laser pulse, a terahertz pulse, you will also have an effect from the time derivative of the magnetic field component. And that is, of course, large when the frequency is high. So you can think a bit about numbers and so on. We implemented this term in our code. We chose as models nickel oxide and cobalt oxide, and look what happens. And what happens indeed is shown here. That is the field, the B field of the laser light for some one cycle or so terahertz laser. The red one, the blue one is the original field. The red one is the field plus its derivative, normalized like here. So it's bigger than. And then we calculated the magnons, you could say, or the magnetization that is excited. We checked also what the effect of the temperature is here. You see the amplitudes are larger. There's of course not a very big effect. There's also some shift, by the way, of the magnitude of the spin wave because of that effect. But it's larger. And now the next question is, how can we maximize that? And of course, what we need is a large frequency and a large prefactor. The prefactor here can be cast in a way like the damping constant. In that framework, the damping is mostly due to the spin-orbit coupling. So one could also say what you need is a large spin-orbit coupling constant, then one would expect large effects. What we tried is these two things, nickel oxide, cobalt oxide. Cobalt oxide has the higher frequency, so that gives a bigger effect. Here is experiment by Gabral, by the way. Cobalt oxide should have a much higher effect. And if one could scale somehow in other materials also the spin-orbit coupling higher, or the damping with that, then would even expect even higher effects. Okay, so I saw that somewhere there's an archive paper, I think, from the group of Alexei Kimmel. At least they mentioned this. I'm not sure whether they would say they've measured it, but at least they discussed this effect, whether they have seen that. That's very recent. I don't have the reference here, sorry. Okay, the other extension of the LRG equation is notation. That's also in that work by Ritwig Mondal, but that was already earlier work, one should mention. Namely that in the Landau-Lifshitz equation, there could also be a second time derivative, and that gives rise to inertia, and with that to notation. So one could ask the simple question, if the spin is an angular momentum that shows precession, is it like in mechanics? Should we not also show notation, right? And that equation then looks like that. It's once again like the Landau-Lifshitz equation, but then it has also m cross the second order time derivative. In that case, this prefactor is not known. There should be this term in principle, but in Ritwig's paper, at least he did not calculate, or as long since now we have not calculated really the number how this prefactor is. It is a time scale, let's say. There's other work by Tonik et al., where they tried to come up with a number from first principles, and there are also some measurements now where they say they have seen notation. So one has some ideas or so. We implemented that once again in our code, and and we are just about playing around with it, let's say. I can show you first results on the FMR or AFMR in the case of antiferromagnetic resonance. And that is shown here. These are resonance spectra, ferromagnet, antiferromagnet. Green is with notation, with some prefactor that is reasonable, let's say, and red is without. So there's the FMR peak that is hardly affected, green to red. But because of the notation, in addition to the normal precession peak, there's another peak. That's a different scale here, by the way. It's minus, it's negative, and it has a much higher frequency here, terahertz range. That is due to the notation. In antiferromagnets, it's even more interesting because you have more peaks. You have two, always positive and negative. But because of the notation, these peaks are much more affected. So there is a shift of the resonance frequency. And also there's less dissipation if you look at that. So the width of these curves goes down as well. And then you have also additional peaks, of course, because of the notation. Once again, they are in the higher frequency regime, and in that case, much larger. So we would say it might be interesting in the future to look also into antiferromagnets. It might be easier to get some knowledge of these notation effects there, because it seems the effects are bigger. And of course, there might be additional effects. So we are currently working on that nonlinear effects and so on. So I think there's a lot of opportunity here. Okay. And with that, we come to the last part, which is the transfer of spinning angular momentum into the lattice. And that is work which was done mostly by Martin Evers here in my group, the theory part. But it's also a collaboration with Peter Baum, also at my place, Constance University, who did the measurements, electron diffraction measurements. So coming back to that problem here, ultra-fast demagnetization. There is this old riddle, what is the flow of angular momentum during these experiments? If you assume that in the total system, in the sample, with all its degrees of freedom, electrons, phonons, spins, the total angular momentum is conserved. Then, because of the demagnetization by 50%, the same amount of angular momentum has to go somewhere. That's, of course, an old question with many theories, and I think most of them are not really satisfying. So on the same time scale, it must go somewhere. And there are some hints now that on these short time scales, it could go somehow to the lattice. And there's a brilliant experiment that Peter Baum and mostly Sonja Tauchert did. That is a time-resolved electron diffraction on a nickel sample. So you get, as quantity, you get Bragg spots, let's say, but time resolved. So you pump with a laser pulse, that means you demagnetize, and you see with that time resolution here what happens with the Bragg spots. And what they measure is, in short, that you have a very fast decay of the intensity of the Bragg spots. And that is normally a measurement of heating, you could say, according to the Debye-Waller theory. That means you have a broadening of the lattice positions, heating phonons, you could say, and that leads to this loss of intensity in the Bragg spot peaks. And the time scale is less than a picosecond here. Okay, that's already rather interesting. But we wondered whether one could even somehow see the angular momentum of the lattice of the phonons. And what we did theoretically or in simulations is the following. We assumed we have a nickel crystal. And what would happen if the angular momentum goes into the lattice? We could make the following assumption, that it locally goes into the lattice so that the spin angular momentum is taken over by an atom, leading to, let's say, an orbital dynamics that then launches a phonon dynamics. And you can simulate that. We did that with the molecular dynamics, used a free software for that, LAMPS. We simulated nickel quantitatively, and the nickel potentials are implemented there. So all we did is we assumed that the demagnetization leads to this displacement of the nickel atoms and some starting velocity so that it takes over 1 h bar of angular momentum. Then you can calculate how many atoms you have to excite corresponding to 50% demagnetization of nickel. And if you do that, you see, of course, that the velocities are no longer isotropically distributed, because the plane of the motion must be perpendicular to the original magnetization or demagnetization, if you want. Okay. So in that picture here, for example, if the magnetization was in that direction, then all angular momentum must lead to a motion in the exact plane. That means X and Y give different results, and the electron beam comes from the top. Okay. That is the anisotropy of the velocities. You could say that is a violation of equipartition theorem, right? Because normally you would say V square and Vx square and Vy square should be equal in thermal equilibrium. So on shorter time scales, you have a violation of equipartition. And that leads to different Bragg spots intensities. If you look at this geometry here, the actual mean comes from top. That means that normally equal Bragg spots like 2, 0, 0 and 0, 2, 0 should be different. And in simulations, it looks like that. So we see a difference of, let's say, 1 to 2 per mil or so. And that can indeed be measured, and it was measured. And this is the measurement result. That is now this ratio. So in the measurement, they did the same. They defined the magnetization direction. Then they know which Bragg spots could be different. You measure here 2, 0, 0 and 0, 2, 0. And you see that the ratio after the laser spot has hit the sample changes. And it changes by the same amount, like in the simulations, 1 to 2, let's say, per mil. And you can do even more in the experiment. You can turn around the magnetization 90 degrees, and the argument changes, which spot should be bigger or lower, and you get these curves here. So I think that is a nice experiment showing that there is an ultra-fast transfer of angular momentum from the spin system into the lattice, and it takes roughly only the same time scale than the demagnetization itself. And I think that is a nice playground in the future. But what it means is that we have excited phonons, not only ultra-fast, but also certain types of phonons, those which are only, that carry an angular momentum. So we call that chiral behavior of the phonons. And it might well be, or we hope that this might be even exploitable somehow, that the phonon is a carrier of angular momentum. There's another paper here that I would like to mention. They made a corresponding experiment. At least it also says that the transfer somehow into the sample of the angular momentum is very fast. They call it ultra-fast Einstein-de-Haas effect. I mean, that's not the same thing. Einstein-de-Haas effect would be that the whole sample rotates. That happens in the simulations, by the way, as well. So in the long run, because we simulate a nanoparticle, the sample in the simulations will rotate, but it takes much longer until you see that. So my last slide, I promise. That was not Landau-Lifshitz equation, even though my title was Landau-Lifshitz equation. I talked about phonons now, but that should be coupled to the spin motion. Spin and lattice should somehow be coupled. And I think that is an important trend maybe for the future. And we started to work on that some time ago, together with Roy Chantrell, by the way, who's still working on that. There's this paper here also, and that is Roy Chantrell's group here. We published some results here. The idea is that you simulate the spin and spatial degrees of freedom at the same time and with the same framework, let's say. Well, that's the idea is you write down a Hamiltonian that contains spin degrees of freedom, like usual, Zeeman coupling, lattice degrees of freedom, momentum, potential, that here creates, this part would create a normal molecular dynamics simulation also. It creates a lattice. And then you need some coupling. And then you should have a framework for spin lattice simulations. So you derive then the equations of motions. And here is once again a bit of Landau-Lifshitz equation, at least the precession part comes out. However, not the relaxation part, because that you don't need anymore, because the relaxation here really goes into the lattice degrees of freedom. So you don't need a heat part, you don't need stochastic equations of motion. Here really the spin degrees couple to the lattice degrees of freedom, and you naturally get a damping into a phonon system just by this coupled equations of motion. So no heat path is necessary. And we tested that, of course, we're still maybe in the test phase, by calculating thermal equilibrium properties. That's one test here for some material, I think it's close to iron or so. We calculated the magnetization versus temperature. We did it with the stochastic Landau-Lifshitz equation, red points, and then with this new framework, and we get practically the same results. That's very promising, and it's not trivial at all, because it is so different. If you do this, really, the simulations are so different. The one is stochastic equations of motion in a canonical ensemble with the heat bath. The other is microcanonical. There is no heat bath, and with a lot of lattice degrees of freedom, but still you get practically the same results. Not regarding the dynamics, but I think I don't have the time to go into details here. The dynamics is quite different. That is interesting. And the weak point, maybe at the last point, is this here, the coupling. So we assumed something that makes some sense if you think about it. It transfers angular momentum and energy from spin into the lattice and the other way around. But you have seen in my talk that I'm very much interested in these multi-scale modeling aspects that you can treat, that you combine different methods. And I would like a more basic or derived from first principles term here for the coupling and for its strength. So this is a bit vague, I would say, at the moment, but I think a very promising idea. So with that, I come to the end. Thanks to my group, to everybody, for my many collaborators. In this talk, important were especially Martin Weinhold, I showed some experiments, and Peter Baum, experimental work, and Karel Carver and Peter Oppenair for the lots of initial calculations that went into this. And of course, I thank all these funding organizations who fund my work. I thank you for listening. And I think I will not go into this summary, but I just put on the last slide to remind you what I've talked about. So thank you very much.
Thank you very much, Ulrich. That was a great talk, as always. Nothing else expected. Let me let me start the round of questions. So we have a few already written, and of course, whoever wants to also ask questions, please go ahead and raise your hand as well. It's also a different format, both work. Could you please go ahead, Niklas, and ask your question?
Hey, sure. Thanks for the nice talk. So I actually have two questions. First, and I think the first part of your presentation, you showed how these orbital resolved spins and like how the interaction, you get these two different demagnetizations. I forgot which element or materials those were, I think.
Rhenium and terbium.
Ah, right. So are those localized moments, or should I think about this as an itinerant system? Because usually the first thing you do is like you take an effective spin per atom, right?
Yeah, that's what you normally would do, and we split that. Yeah, some people could think that this kind of modeling is a bit overstretched, let's say. But indeed, I mean, this very old work from Lichtenstein, Katzel, that's already there. It's just nobody mentioned it so far, but it's already there. That if you calculate these parameters, they are orbital wise. So you get really exchange interactions per orbital. And of course, whether the moments are more localized or not goes into that calculation, or it is a result of that calculations. And it's indeed so because the, or maybe we take this picture here, because of the F orbitals, they are very localized. There is, for example, no exchange interaction between F orbitals. So the Heisenberg exchange is zero here. That's only via the less localized moments or via the SNT. Here you get exchange integrals, but you get also an intra-atomic exchange integral. So effectively, everything is ordered so that you get a ferromagnet at the end out.
I see. Okay, thanks. And as a second thing, in your last slide where you showed that basically this coupling to the lattice corresponds to what you would find, yeah, right, this on the upper right-hand corner, that you get a similar behavior as when you couple it to a heat bath. Does that depend on the coupling? If I would put something else, does it change?
No, well, I would say it should not, because okay, that is tricky. I mean, what can one expect, right? One could say statistical physics should tell you whether you are in a micro-canonical or canonical ensemble should not matter. And as long as everything is right, you should get the same result. You could probably make mistakes with that form of the coupling. I mean, what you need is it transfers angular momentum and energy and keeps both in the total system constant. That's you have to take care of what we did. I mean, that's not easy to see, but that is so. Then I would say it should be equal unless you have some additional effects. I mean, one has some additional effects here, by the way, because of the lattice fluctuations. You could say the lattice should expand. If the lattice expands, so the exchange is altered, and then you might have a slightly different TC. So it would maybe even make sense that there are smaller deviations, but this effect is very small. That would be maybe a percent change or so of TC, and that is beyond what we tested here. So there might be really additional physical effects, of course, but in principle, we should see the same behavior. Yeah.
I see. Thank you very much.
Good. Let's move on to Mikhail.
Can you hear me?
Yeah, we can hear you.
Thank you. Uli, nice talk. I just have one of my fantasy questions again. Okay. So right up to now, we are considering the magnetic moment as constant across the atomic volume, as I understand it. Now, with all these ultra-fast techniques and ultra-high or intensive laser pulses, should we start to consider that as the pulse moves through, that we have a magnetic gradient magnetic flux across the atomic volume?
Okay, that's a difficult question, let's say, which has probably different answers on different levels. Maybe I'm looking for a slide that I could use here. I mean, first of all, if you do this type of modeling and you distinguish F and T electrons, then the total magnetic moment across even one atom is no longer constant, because that can fluctuate already, and the F naught, that's what is measured. So in that model already, the total magnetic moment is no longer constant.
Okay, so then you create a huge gradient across the atom.
Inside the atom. With the intraatomic coupling involved, that is, by the way, high, but it's not not infinite. It's a bit higher than the D exchange or so, but it's not infinite.
The distance
can do that in experiments.
The distance is very short.
And then, of course, not to forget that there are materials which are not good Heisenberg models. I mean, there are materials where the magnetic moment is not very constant anyway, like, for example, nickel is not a good Heisenberg model. And then there is things like iron platinum, where the platinum has some magnetic moment, but it's induced by the iron. And then it might go away. So it's not that always a spin model assuming constant length is good. I mean, there are counterexamples, of course, and one has to discuss that material dependent.
Okay, thanks.
Okay, let's go to Martin Eschliman. Martin, go ahead and ask your question, please.
Hi, Uli. I have a question to the last part of your talk. Can you say a little bit more about the microscopic mechanism, how you can transfer from the spin system and 1H bar to the phonon system?
Yeah, if I would know that, I would have told it.
Yeah, I thought so.
That is really a question, and we didn't model it at all. I mean, to make it clear, we assumed that the effect exists and there must be a motion. Okay, so how that works is not clear at all, and that is a difficult task. I think that one should discuss with people doing, for example, time-dependent DFT or so. They could tell you, I mean, somehow, because of the laser pulse, something will change, the interaction with the neighbors in an atom will change, and somehow some force will act, let's say. But I don't think that is understood, but there might be work coming up, and I would say time-dependent DFT, they could tell us something. But here, we just assumed, on that level, we just assumed that what if it exists? How would the phonons develop? What would it look like? And it looks like in the experiment. So I'm rather positive.
Because when you would have in orbit coupling and you would just switch one spin, you would transfer not exactly 1 h bar. It may be just a fraction of h bar. But that should not be possible to a single phonon. Yeah,
that is possible. We made it as an assumption here. It seems a reasonable assumption, a spin flip, okay? But we played around, of course, in our molecular dynamic simulation with other assumptions. It doesn't affect the results much. I mean, if you would split it and give it 2 atoms or so, probably after 50 femtoseconds, it doesn't matter much. Because the atomic motion is rather quick. It is like you are in the language of phonons, you are at the edge of the Brownian zone. And so they excite immediately the neighbors. And then everything is transferred. So when we are here, and then already you have all atoms excited and you have a phonon system, you could call it, I mean, not an equilibrium thermal phonon system, but you have some kind of phonon system. All atoms move somehow and have taken over the angular momentum. And then they have this property. So I would say the excitation mechanism is not understood completely. But the details do not count too much. I think it is true that it goes into the phonon system on the time scale, but it's an open question how.
Okay, thanks.
Let's move on to Andropov. Can you go ahead? Do you have a microphone? Go ahead.
Can you hear me?
Yeah, we can hear you.
Oh, great, fantastic. I have a simple question. So it's okay, of course, to use spin-only dynamics like Landau-Lifshitz for ferromagnetic resonance and so on. So you are describing laser excitations. So this excitation is much more complicated. It involves charge, spin current, and magnetization excitations, and they are coupled. Moreover, all scales are involved here, and magnetization is not really kind of slow because it's fast charge dynamics, which determines like everything. And of course, ab initio, let's say, density functional has all these dynamic equations and blah, 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 and you can add temperature for the charge and so on. But where, and I don't understand where charge and spin current dynamics in your equations, because it's Landau-Lifshitz equation only.
Yeah, that's true.
And charge is different, and it cannot be described by slow Landau-Lifshitz equation at all. It's more complicated dynamics.
Yeah, okay, I understand the question, but I do not agree that the Landau-Lifshitz equation is slow. It is as fast as simulated, right? I mean, that's
it's how it's derived. It's how it's derived from density function. If you derive it, you see you are doing this approximation. So you must have charge excitation there, because charge transfer laser doesn't care about magnetism very often. It just transfer electron to D to S, let's say, and so on. And it's really fast, and dynamics simply follow. Roughly speaking, it's like you want to describe how car is moving when there is an atomic explosion nearby. And if you ignore atomic explosion, you cannot really say much. It's not fast dynamics. Magnetization dynamics is slow. It's just charge makes fantastic dynamics for the magnetization, but spin is just follow.
Yeah, so okay, let's take this picture here. So that is the simulation, the solid line. So the question is, where is the charge, for example, or the electrons on our simulation level here on that time scale, why it decays, right? The point is, in our modeling, it is all just in the temperature of the heat bath.
Yes, I know, but
so it seems to be
so
sufficient to assume that the electron excitation leads to a temperature rise in the heat bath. Of course, that's not perfect. I mean, I would also like to know everything at the same time. It's a bit difficult, but of course, it would be interesting to get a better picture of the electronic excitation, better than saying it has a temperature which is high. Of course, on a very short time scale, that's not true. One would say, yeah, there are certain energy levels more excited than others, and it takes some equilibration time until you can even define an electron temperature. And that is indeed beyond what we are doing. So we assume you can still say it is only a high temperature that leads to fluctuations. Okay. If you want to know it more exactly or more based on first principle, then you are right. Then one has to use a different framework that takes the electrons more explicitly into account.
Okay. Thanks. Let's move on to Dingbin. Go ahead and unmute yourself, and then next afterwards, Matthias.
Yeah, thanks for the great talk. My question is regarding the inverse Faraday effect. So when you use this effect to switch the magnetization directions, how to understand this from the perspective of conservation of angular momentum? Are the changes of the angular momentum of the magnetic system purely come from the angular momentum of the light, or it also comes from other sources?
You mean in that case here, the inverse Faraday effect?
Yeah.
Okay. So let's take this picture here. So because of the inverse Faraday effect, there is an induced moment. And now your question is how that goes along with angular momentum conservation?
Yeah.
That is a good question. I have to think of it. And first of all, I would not say that during the laser pulse, the angular momentum has to be conserved. I'm not so sure. And that moment, while the pulse is there, you have an open system. At least you don't have a closed system, right?
Mm-hmm.
But okay, I'm not sure that this is best answer. I think that's interesting. I'm not sure that I can answer that well. I mean, when you calculate it from first principles, the question is what assumptions you make at that moment. The induced moments is partly in the spin system, I think also partly in the orbital system. I must say I don't know whether that is what that means in terms of angular momentum conservation. I'm sorry, I can't answer that. But that should be asked to Peter Oppenheim. Maybe he has an idea.
Okay, we'll ask him to if he's still around. He was around earlier.
Is he around? I should not refer to the audience.
I'm not sure if he's still there. Hang on. Hang on a second.
But I agree.
Peter, we're going to put you on the spot. So can you please answer the question?
Yeah, can you hear me?
Yeah, we can hear you.
Perfect.
Okay, yeah, it's a good question. And actually, one has to see now that the inverse Faraday effect is different from the absorption. Okay, so the absorption, which is a linear effect, would give a difference if you have different helicities. However, that difference is 0 for an antiferromagnet. Okay, but the inverse Faraday effect is like it is like a Raman process, and actually then there is no transfer of angular momentum of the light. Okay, so the sum that we get in the calculations for the two atoms, they cancel each other. There is one moment up and there is one induced moment down, and the total is 0.
Okay. That is for the anti-ferromagnet case.
Yeah.
Okay. All right. Thank you. That was very good added value. So if it's okay, let's move on to Matthias.
Yeah. Thank you.
Thanks, Peter. That was very on the spot.
Hi, Uli. Very, very exciting talk, very exciting discussion. Now, one of the things that we're working on, which seems to be quite relevant, or that your calculations can be relevant for, is this Magna and Phonon polaron formation. You know, there are all this original work from Ichizaitos group, where if you apply a certain field, you can make the magnon and the phonon dispersion relations touch, and then you get this enhanced transport. Is that something that you could calculate? Because there are some ideas which maybe I should, you know, there's only friends here, so I can tell you all the ideas. But
okay.
you know,
that refers probably to that slide.
Mm-hmm. Yeah,
I'm not sure about the polaron part. That's not included here.
But just magnons and phonons that together then hybridize as polarons.
Yeah, the magnon-phonon part should be in here. Yeah. I mean, as I said, the weak point is at the moment to quantify or to better form of the coupling constant of this spin lattice coupling. But apart from that, yes, we should see.
So maybe we can get offline on Skype to discuss that, because I think there are some interesting ideas or some calculations. But yeah, I think it's really bringing us forward, a step forward towards a more realistic description. Thanks.
Okay.
Let's move on next. Try to get to everybody. There's lots of questions today, so that's great, wonderful. With 250 people that showed up. So let's have Branislav. I think you can now talk. I think you have a comment. Or things you want to share with us. Branislav.
Yeah. Can you hear me?
Yeah, I can hear you.
Yeah. So I just wanted to make a comment and then ask the follow-up question on this topic of essentially how do electrons respond to this local magnetization dynamics while not going into full TDDFT. So obviously, when these local magnetic moments start moving, they would be pushing any kind of surrounding conduction electrons out of equilibrium. And these surrounding conduction electrons being out of equilibrium are going to exert additional damping, and they're going to pump all kinds of currents. And now the question is, this effect actually becomes very important in the non-collinear systems. So if you have any kind of texture and the small magnetic moments are driven, let's say by femtosecond pulse or by external fields, they would be moving and they would be jerking this C of the conduction electrons. And then the question becomes, this was this question like 2 questions ago, you know, what do the electrons do? And they're obviously not in any kind of micromagnetics or atomistic spin dynamics. And then the question becomes, can you take these effects into account, which would mean basically that you have to add something into your LRG equation, which is beyond all these terms you have discussed. And there have been attempts since, let's say, mid-2000s. There are papers by Nagaosa, Franson, and several other people, Potohov, including us as well, to actually integrate out these electrons. Integrating out means you start from some theory which takes both electrons as quantum described particles and these local magnetic moments, and then you manipulate these equations until you get rid of the electrons and you produce a formula which you could plug into your LRG equation. But according to some analysis by Potohov as well as us, that is not possible in every regime. Like depending on the speed of this motion of localized magnetic moments, it looks like that at the end of the day, you have to kind of do self-consistent coupling, which means that you have to run in those situations when these conduction electrons are relevant, at the same time your LRG and these quantum electrons responding to this motion. And so the question basically is, have you ever encountered these situations? In other words, have you applied this extended type of LRG equation to situations when you have this non-collinear spins that would introduce this? This is a topic of essentially what is called non-local damping in non-collinear magnetic textures.
No, we have not tried that, but it is certainly interesting. But maybe on that occasion, I should point out that, for example, in these kind of calculations, let's say the demagnetization in gadolinium terbium, what you try to explain probably would be that because of the electronic motion, we would have in our language an enhanced damping or a change of fluctuations or something like that. That would probably be the way you model it. The point is, it seems on that level not yet necessary, because the damping parameters that we use are the same that you would have in equilibrium. That is, while what you are describing looks like that one would have to alter the damping parameters somehow, for example, or one would have to alter the noise properties. That is something some people work on, going beyond, let's say, white noise, which is a simple assumption. That might be interesting, for example, correlated noise. Or, of course, if you really know what the effective fields from acting from the electrons would be on some time scale, that one could, of course, implement somehow, yeah. So it's all interesting, but we haven't tried, not beyond this white noise assumption with the same damping parameters that you use for equilibrium or from experiments.
Yeah, that's exactly the case. It would look like there is your standard Kilbert damping, the equilibrium one, which comes from some DFT theory, which includes spin orbit coupling and Phonon effects, and there is another damping which is purely dynamical non-equilibrium effects. And by the way, in the paper,
yeah, of course, we could implement it. A time-dependent damping also is not really a technical problem. We would need some knowledge, what's some collaboration. Let's say it can be implemented, of course.
Yeah. So at the end game looks like as if you have extra damping, which depends on time.
Yeah, okay, I see. Yeah, could be interesting, but I haven't tried so far.
Yeah, I'll send you some papers just to take a look, because Potohov has done something of this kind. I mean, what you really get is you get a time retarded LLG equation with non-Markovian kernel. And then when you expand that kernel, you actually pick up this extra damping, which is depending on time. And that appears in papers by Potohov as well as in our own.
Okay, thank you. Yeah.
Good. Let's go to next to Igor Sandalov. Go ahead and ask your question.
Can you hear me?
I can hear you. Yeah, I can hear you.
Yes. Okay. First, since my question is to the same basket about the role played by conduction electrons in this exchange and so on, it's also concerns this Bronislav comment that actually it looks like there should exist some separation in time scale, because electrons form temperature much faster than all other processes, it looks like. But as for exchange interaction, then in metals and in insulators, it should be different. And in metals, when you excite very fast electrons, it's not only decay which is changed, it also strongly changed exchange interaction, because involved excited states provide you completely different exchange interaction. So it looks like it's not sufficient to insert there just different decay, maybe time-dependent decay even. So main question is, what would be the difference between description of metallic and insulating magnets?
Okay. On the level, are we simulated? It's not a difference. It is all, I mean, the difference would be that the electrons are less heated also usually in an insulator. But it's not really a fundamental difference on the level of the Landau-Lifshitz equation.
Okay, but
what you say regarding the exchange constants, I know there's a lot, there's some work going on that everything is altered. And we try from time to time. The point is, it doesn't make a big difference in the simulations. For example, if you assume that an exchange constant breaks down by 20%, that doesn't matter at all, honestly. It would change the Curie temperature, of course, accordingly, but you are above that maybe anyway for some time. That doesn't matter much, unless you have very special systems where the ground state is an imbalance of Jaruzelski-Maria and exchange interaction, and then if that ratio changes, then you will excite something. But a pure variation of magnetic moments or exchange interactions doesn't affect much the dynamics.
Well, that's, I believe, because in left-hand side, you have just a second derivative, which means small k expansion for spin waves. But spin waves will not describe everything.
Well, that's what he referred to at the beginning of the talk as well, Igor, that
okay, yeah.
the high temperature introduces the full spectrum too in this in the spin models. Yeah?
Okay, thank you. Yeah.
So let's move on to Mark, so to fit everybody in. Mark, can you unmute yourself? And I think you should be able to talk if you would like to ask a question. Mark Auslander.
Okay.
Yeah, go ahead.
Yes. My question is as follows. Thank you for a nice talk. Don't you think that the corrections to the torques proportional to magnetization's time derivative you revealed are the manifestations of non-Markovian retardation effects beyond the LLG paradigm? Actually, Branislav asked, stated this in his question.
So do I understand you correctly? So you refer to the second order time derivative. Oh no, the field derivative talks, right?
Yes, first derivative.
Maybe we put up that slide. Was it that one? Right. And now your question was whether that leads to non-Markovian processes.
Yes. As it looks like, it is Markovian, local in time, but because you have a derivative and for h, so it may be, I don't know.
So I haven't thought about that, I must say. So what would I have to do? I mean, would we see that? Or
okay.
So we haven't tried, and I'm not sure how to answer.
You don't have to do anything. Simply, I refer to, there was some paper in 60s by Provotorov in Physical Review, which tried to derive Landau-Lifshitz equation for some simplest system in the spins interacting with exchange and dipole-dipole. And from this derivation, from density matrix approach, they obtained that there is a retardation, should be retardation, and retardation, when you, the retardation should be with respect also to h, because the kernel of the damping term involves h and m. Derivative of m you can exclude using the Gilbert trick. So express them via cross product, but derivative of h, which emerge if you expand the kernel, I think that this is something like you revealed theoretically and experimentally. It's only comment.
Okay.
Okay, so let's move on to, I think also Peter had a,
thank you for the comment.
Read it a little bit on the, with you, he had written a comment in the Q&A following up. So Pinto, go ahead and ask your question, and we'll try to keep a couple of more questions, but keep them short, please.
Okay, am I audible?
Yeah.
Yeah. Okay. Thank you. It's a very nice talk. So I have one question. This is regarding the spin lattice coupling that you have discussed. So is it possible that because of the coupling of some finite coupling constant, the spin wave mode and phonon modes are excited exactly at the same frequency? And if yes, does it also depend on any critical coupling strength?
Yeah, I think, yeah, sure, that's possible. I think that's what some people are looking for. Crossings of the dispersion of more magnon and phonon. And well, your question is, would that depend on the coupling? No, I wouldn't say so. Once you assume that you have dispersion relations for both, let's say coming from that part of the Hamiltonian, then you switch on a weak coupling, then you would say that there should be a resonant coupling or so. Yeah, that would not really depend on this. Yeah, as long as it is reasonable, it should be there, let's say, and not depend on the strength of the coupling, I would say.
Okay.
Okay.
And Mikhail, can you go ahead and...
Hello, thank you for the great talk. And my question is about notation. And I would like to ask about can notation and antiferromagnetic resonance interact with each other, and how this interaction can occur here, can happen. Thank
you. You refer to this slide, I think.
Yeah.
And your question is, was it for the antiferromagnet or ferro?
For antiferromagnet.
For the antiferromagnet. Okay. And you say there's an interaction. What would you say? The interaction between the notation and the precession resonance peaks or so?
Yeah, can they be so close that even overlap with each other?
Oh yes, sure. I mean, the big point here is the value of the coupling constant, and with that would affect it. And in our case, here they are quite separated, but I wouldn't say that it's necessarily so. The other question is, what is the reasonable value of this coupling constant, which in our case, by the way, is in units of a time scale. It's here 10 to the minus 13 seconds. Of course, if you make other assumptions, the notation peaks would go elsewhere. They could go to the other peaks that overlap. But I think that would be an unreasonable assumption for the value of eta. But I'm not sure that this is necessarily in all materials. So I'm not sure. But for that, how we started, it would be a rather unreasonable assumption for eta.
Oh, thank you. Thank you.
Hopefully, if you have still a little bit more, let's say Sayed Hussein, can you go ahead and ask a question? Short one, please.
Yeah, thank you very much for the very nice talk, actually. So I have one question regarding the same slide, the notation.
Yeah.
So the origin of the notation in ferromagnet and antiferromagnet are the same, and the second is very basic. So what is the origin of notation actually? Or the inertia. So very basic thing. That can you explain? Because in ferromagnetic resonance we normally observe a simple absorption spectrum. But there is a nature physics very recent only one experiment report on this notation.
Yeah, so, this one here, I guess.
Yeah. So can you explain a bit more explain how this notation comes in ferromagnet and antiferromagnet, or are these different or the same?
Mm-hmm. I should say that I'm not an expert in the derivation of this equation. That's not my work. That's Ulrich Mandal, who has one derivation of this term. I mean, the result is a second order derivative, and that gives rise, of course, in analogy to other equations of motion, to the inertia and the notation. Is of course, I mean, that derivation, it has a relativistic origin because that's the way it was derived. Whether one could say it is, it is certainly not a difference, by the way. That was one of your questions, between ferromagnet and antiferromagnet. I mean, that is on the level of that derivation, there was no assumption made whether you have a ferro or an antiferromagnet. So we just use that equation for both. here, but it's not a basic difference made. A simple picture where it comes from, I mean, hard to say. I mean, mechanically, it means that, how to express that, that the angular momentum is not aligned with the rotation axis. That's what it means mechanically. What that means in terms of spins and orbits is hard to say. I don't have a simple picture for that.
Okay.
But mechanically, I'm not sure if that is a good answer. But mechanically, it's exactly that the rotation axis is not the angular momentum, one of the main axes of the or is the axis of the angular momentum. Then you get this notation.
Okay. So let's have two last questions. So we'll be short. Sumit, go ahead and ask your question, and then Dan after that, and then we'll stop there.
Thank you for the nice talk. I have a quick question about laser-assisted dynamics. So the way you introduce laser is through its magnetic field. Is it also necessary to include the electric field, or one can safely ignore that?
Yeah, yeah. The laser is taken into account in two ways. I think that refers probably to, or in many ways. It depends on the problem you're talking about. Maybe we go for this slide. I don't know. I mean, one way is to take the heating into account. I would say that is the electrical field. I mean, you would say the electrical field excites electron, the electrons heat, and for us, then it is a heat bath. Okay, so the electrical field is the heating. Okay, the magnetic field would go in this terahertz excitation if it is large. Normally it is small. But then there are also other effects that have, of course, to do with the electrical field, like the inverse Faraday effect. But that is taken into account effectively by this induced moment.
Okay. Okay. Thank you.
Yeah. Okay.
Yeah.
Great. Dan, go ahead and are you able to ask a question? Not sure if he can unmute himself.
Oh, sorry.
Go ahead.
So I guess, like, with regards to the demagnetization, I was kind of curious as to how, like, the different orbitals were probed, like experimentally, like the 4F and the 5D and the 6, or yeah, the 4F and the 5D.
How that was done experimentally? Yeah, so I'm not really the expert in that, I must say. I'm the theoretician. That was done by Martin Weinl. So what they did is photo emission, and they made measurement of the exchange splitting and magnetic linear dichroism, and in the same setup. But don't ask me details, I'm sorry.
All right, so we'll ask Dan to refer to the experimentalist then to find that.
If he's there, yes, I would love to.
No, I think everybody, well, actually, many people stuck around, but unfortunately, we really over time. So with that, I think I'm going to conclude today's, let me stop the streaming.